This is lecture number 10 in the respiratory system, and throughout all the respiratory system, this is probably my favorite section. We're going to talk about this thing called the hemoglobin dissociation curve and what it means to shift the curve to the right or left, as well as what these different substrates what kind of effect that will have on the curve. And the reason I like the hemoglobin dissociation curve is that there's a lot of stuff here that is actually not intuitive. And I love reading about and hearing things that are not intuitive because it really makes you dig in and expands the way that we think about physiology. And so this is a great example. So let's get into it. First off, we want to understand hemoglobin. You already know the basic details about hemoglobin. You know that it has a quaternary structure and there's 2 alpha chains and 2 beta chains. Now, realistically, the fact that there are 2 alpha chains and 2 beta chains for everything we're going to talk about is completely irrelevant. That's just kind of trivia that you learned during blood. Now you know it. I just wanted to label it just to remind you. You also know that each of these chains carries with it an oxygen molecule. So hemoglobin, a single hemoglobin molecule can carry with it 4 oxygens. So there we have it. Okay, so there's a general review for what hemoglobin is. You also know based on previous lectures in the respiratory system that you got to have hemoglobin because these are the boats that carry oxygen. And without it, we just can't carry a very big load of oxygen in the blood. Sorry, great, we got that. So now, what I want to do is just to kind of make life simple, let's ignore the fact that these are 2 alpha and 2 beta chains. Let's ignore the fact that it carries 4 oxygen. You already know that. And just to make the math simple for what I'm about to show you, I want to say that this is a hemoglobin molecule and it only carries 1 oxygen atom. Okay, just to make the math simple. Again, you know the reality. It carries 4. Did I say oxygen atom? I take that back. It's oxygen molecules, pardon me. And so you already know that hemoglobin carries 4 oxygens. That's why we reviewed that. But just for, again, a simple approach for the next few slides, I want to show you that this is a single hemoglobin molecule. I'm just smushing all these little polypeptide chains together to form this. This is a single hemoglobin and it's carrying 1 oxygen, okay? So with that in mind, then here's what I'm going to show you. Let's go to the next slide. When you look at this, what I want you to see is that in this slide, what we actually have is a 10 by 10 matrix, and I have 10 hemoglobin molecules across 10 down for a total of 100 hemoglobin molecules, each of which are carrying an oxygen molecule. All right, so what does that mean? It means if you were to sit there and count that we have 100 oxygen molecules on here. Again, 100 hemoglobins and 100 oxygen molecules. So the term that I'm going to use now is this. This is the term that I'm going to use. I'm going to say in this situation, we are in a situation where we have 100% hemoglobin saturation. Now, saturation with what? Well, it's saturation with oxygen. Oxygen. It's saturation with oxygen. So I have 100% hemoglobin saturation, meaning that every single hemoglobin molecule here is carrying an oxygen molecule. Okay? So hopefully that makes sense. When we look at something like this then, what do we have here? Well, I'll just tell you, here you have 75% hemoglobin saturation because what I did, I took the top 2 rows, that's 20, 21, 22, 23, 24, 25, and I removed oxygen from those. So now I have 75% hemoglobin saturation. All right? I need to throw a term in for you, and that term is dissociation. Whatever dissociation means, it means simply this. Let's look. Right now, my hemoglobin molecule is associated with oxygen, and right now it is disassociated. Okay, so this is hemoglobin dissociation. It simply means hemoglobin molecule unloads oxygen. That process of unloading oxygen is called dissociation. And that's why we have this thing called the hemoglobin dissociation curve. So what are we really saying? In this whole curve that I'm about to show you, we're really talking about hemoglobin unloading oxygen. Well, that's a good thing for us, right? Because again, why is hemoglobin picking up oxygen at the lungs? So that it can unload it at the tissues, right? You know that already. One more time. Why is hemoglobin picking up oxygen at the lungs? So that hemoglobin dissociation with oxygen can occur at the tissues. Okay, so again, there's really no new information here for you so far. The only new term is dissociation, and now you know what dissociation is. Here is association, dissociation. Association, dissociation. Pretty simple. So what do we have over here? We have 25% of my hemoglobins, which is 25 out of the 100 here. That's 25% of my hemoglobins have dissociated, have unloaded oxygen, presumably unloaded it to the tissues. All right? When you look at something like this, what do we see? Well, here we have 0% hemoglobin saturation, right? In this particular scenario, every single hemoglobin molecule has unloaded its oxygen. Now, Here's what I want you to think of before I show you the curve. I want you to make this make sense. Right over here, 100% hemoglobin saturation. Where do we see that? Do we see that at the lungs or do we see that at the tissues? When I'm looking in at my hemoglobin, at my blood, where do I see 100% hemoglobin saturation? Here at the lungs, so let's say right over there, or right over here once I've done unloading. So your intuition would tell you, well, I would assume it's going to be at the lungs where I have 100% hemoglobin saturation. After all, my deoxygenated blood came to the lungs so that it might pick up oxygen, right? You already know that. So now here's the next thing. Where might you see hemoglobin, a 0% hemoglobin saturation? In other words, no oxygen bound to hemoglobin. And again, if you're making a guess here, if you've not read ahead, if you're making a guess, you might think, well, I suppose that would be after I unload, after I dissociate, after hemoglobin dissociates from oxygen, and after I unload at the tissues. That would seem to make sense. But wait a minute though. I actually still have some oxygen here in my systemic veins, right? So you're guessing if this thing were to occur, then if it were to occur anywhere, it might occur right over here where you have 0% saturation. But you're thinking, no, that can't possibly be right because I actually still have a PO2 of 40. Which means then my systemic veins are carrying, yes, they're carrying the deoxygenated blood. But by deoxygenated, do we really mean completely deoxygenated where it's 0% hemoglobin saturation, or do we mean something else? And I'm going to tell you that this situation, it doesn't occur. The reality is you're always going to have some oxygen molecules loaded up onto hemoglobin, even in your deoxygenated blood. Now, I'm just throwing 3 here, but my point is you're always going to have oxygen in your blood, even in your veins, even in your deoxygenated blood. Well, how much then? I get it that the PO2 is 40, but how much hemoglobin is holding on to oxygen? And maybe you're thinking, well, if it's 40 millimeters mercury, it was 100 millimeters mercury here, maybe 40? And that'd be a good guess. You know, if you're gonna guess, if I said how many of these are holding on to oxygen, I guess the best guess would be 40, but it's not true. Let me show you the hemoglobin dissociation curve now, finally. There it is. Thing of beauty. What I want you to do is freeze the video, pause the video, and take a look at this and just read it out. Again, anytime you see a plot like this, you just read it out, even if it doesn't make perfect sense. So let's do that together. You'll say, well, on the x-axis, I have PO2, partial pressure of oxygen, and I've got some numbers that I recognize. I recognize the number 40 because that's the PO2 of a resting cell. Remember, that's the tissue PO2, and I recognize the number 100 because that's the PO2 at the alveoli. Again, 100, 104. Again, we're going to just smush those together. On the y-axis, what I have is hemoglobin saturation from 0, way down here, to 100. Well, now you have a visual for what that means. 100% hemoglobin saturation means this, right? This scenario right over here. 0% hemoglobin saturation means, let me erase these, this is 0% hemoglobin saturation. All right, so now we have our bearings. On the x-axis is PO2, and the y-axis is hemoglobin saturation. So now, when the PO2 is at 100 at the alveoli, this curve is telling us the hemoglobin saturation level. And at 100 PO2 at the alveoli, the hemoglobin saturation is, according to this slide, about 98, 99%. And again, just to make the numbers smooth and easy, we're just going to say it's 100%. At the lungs, you have 100% hemoglobin saturation. What we talked about before, a moment earlier, your intuition is correct. When the blood is entering into the pulmonary circulation, and it enters into pulmonary circulation, it goes into the lungs, oxygen diffuses, it goes on into the blood, oxygen binds onto hemoglobin, and now the oxygenated blood is leaving the lungs. Well, what is the hemoglobin saturation of oxygenated blood? And your answer is going to be, it is 100% hemoglobin saturation. And when we see 100% hemoglobin saturation, that is what's going to also relate to the PO2 of 104 or 100. Okay, so there we have it. Full saturation at the lungs. No surprise here. You already knew hemoglobin picked up oxygen at the lungs. Now, here's the interesting part. When you go down to the resting cell, in other words, when I come down here and the resting cell, it has a PO2 of 40. I know it says less than 40. We'll get to that another point, but let's just say it's 40. When the PO2 is 40 here, hemoglobin is going to unload oxygen. Well, what is the hemoglobin saturation when you have a PO2 of 40? Right over here. There's the PO2 of 40. What is the hemoglobin saturation? And if you look at the plot here, it looks like, well, hemoglobin saturation is still 75%. One more time, hemoglobin saturation is still 75% in my deoxygenated blood. When my PO2 is 40, hemoglobin saturation is still 75%. To say it differently, when you travel right over here, when you look at the hemoglobin saturation right over here, what is it? You already know it's not zero, right? We just talked about that. You already know it's not zero, so what is it? Mind-boggling, it's going to be 75% saturation. Again, what I did is I removed 25 of these out of 100. This is 75% saturation. Now look, when you look at this slide here, if I asked you the question very simply, is there a lot of oxygen there or only a little bit? I think most of us would say, well, it looks reasonably well loaded up with oxygen. It's 75% saturated with oxygen, and that's correct. Folks, this is your deoxygenated blood. This right here, 75% saturation. This is your PO2 of 40 millimeters mercury. This is your deoxygenated blood. What that means then is that the blood entering into the capillaries, alveolar capillaries, even though it's got a PO2 of 40, how does that relate to actual oxygen load? This right here is your deoxygenated blood entering into the lungs so that we can refill these 25 seats. Look, this is just nutty. This just doesn't make sense. I think our intuition wants us to think that I pick up a bunch of oxygen, I dump off all the oxygen, and I return to the lungs empty-handed to refill yet again. But what I'm really saying to you is that I return to the lungs 75% saturation. That's a far cry from being empty-handed. And so that is the property, of the hemoglobin dissociation curve. Now, here's what that really looks. If we look at this line, it's got this weird, goofy shape. You'll notice it is not a straight line. And what does that tell us? It tells us that with a significant drop in PO2, what is this? This is a 60% drop in PO2, going from 100 down to 40. With a 60% drop in PO2, I only see a 25% drop in hemoglobin saturation. Okay, let me say that differently. Maybe that doesn't make sense. Maybe that's just kind of reading the numbers and trying to make something that you don't quite get. Here, let's do this instead. Let me draw that line here. Okay, what we have here now is a new line. So I got this purple line here, and what I'm going to say is that, let's say this is your PO2 at the alveoli is 100 in a healthy state. Now, here's what's happening. I have a little bit of asthma. Okay, I have a little bit of asthma, and there's a bunch of pollen out there. I'm reacting a little bit, and I can't quite get the same amount of oxygen I want into my lungs. It's not a severe attack, but now what ends up happening is that the PO2 in my lungs, because of this kind of asthmatic event, and again, I've shown you this before. Let me go ahead and find that picture. The PO2 in my lungs is actually going to be quite different. We talked earlier looking at a picture like this, and we said, well, in asthma, my bronchioles are constricted, so now my PO2 is low. Great. How low is it? Let's just say it'll drop by 10%. Okay, so let's drop my PO2 by 10% in my lungs because I have asthma. So let's come back here. My PO2 now in the alveoli is going to be dropped by 10%. It's going to sit right here at 90. Look at that. Now, here's my question for you. When you look at this hemoglobin dissociation curve, I had a 10% drop in my PO2 at my lungs. What's my drop in hemoglobin saturation? I mean, what is it? Like 4% drop? I still have 96% saturation. That is unbelievably good. Let's give me a more significant asthmatic event now. Now my PO2 has dropped by, here, let's say 25%. No, not 25. Let's say 30%. I'm now down to my PO2 of 70. I'm in my lungs. I've got that attack going. And it really, really stinks. I'm very, very uncomfortable. But how much are my tissues really going to suffer? What I want you to see is that, wow, I still have what is that? Let's say 93% hemoglobin saturation. What that means that at your lungs, even though you've compromised and now you only have a 70 PO2, 70 millimeters of mercury PO2 at the lungs, really what we're looking at then is simply only, let's see, 1, 2, 3, 4, 5, 6, 7, 8. 8 of these are now empty-handed. Oops, that's not what I meant to do. What I meant to do was just highlight the oxygen itself. So this oxygen right over here, that will disappear. That oxygen molecule disappear. That oxygen molecule disappear. So on and so forth until finally we get to, there you have it, 92% saturation. So now I'm at 92% saturation in this situation where I have a significant decline at the alveoli. Understand this: hemoglobin is not alive. The thing's just a protein, right? It's not actually alive. There's no benevolence here. There's no kindness to hemoglobin. All hemoglobin is doing, this is the design of hemoglobin. Under these situations, a significant drop in PO2 leads to only a small drop in hemoglobin dissociation. And that is so that for darn sure we can carry enough oxygen to deliver the tissues. The next part, when we get down to 40, I'm at 25% saturation. Again, what does that tell us? Did I say 25? I meant 75% saturation. I've only offloaded 25%. That means your deoxygenated blood actually carries quite a bit of oxygen in it. That's what this curve is telling us. All right. So I'm gonna cut off the video here, and I'm gonna pick up hemoglobin dissociation curve in a second video, just so we don't make this too long. But I need you to really understand this, that hemoglobin dissociation curve, the design of it is such that a significant drop in PO2 leads to only a minor drop in oxygen saturation, hemoglobin saturation at the upper end. But you'll see that it actually gets steep right over here. So from here, from 40, if I decrease by 25%, okay, go from 40 to 30, I have a 25% drop in oxygenation or PO2, then what do I see? I go from 75% saturation down to 55% saturation, which is a much bigger drop. So this is the nature of the hemoglobin dissociation curve. We'll pick this up in the next video.